Now we learned all about MOSFET transistors. We figured out how to find out if the transistor is in saturation, non-saturation region, and then how do we determine the small signal model parameters for the MOSFET transistor. Now that we have done that, I would like to go through few circuit examples. Just like what we did in the bipolar case, we'll figure out what region of operation the transistor is in, and then if applicable, we will figure out gain of the transistor in that particular configuration. In my opinion, that's one of the most important thing you should know, because as a designer or as an electrical engineer, you should know MOSFET transistor behavior and bipolar transistor behavior, when to use which one, and what are the differences and similarities between the two. We're going to start off with DC analysis for MOSFET. We're going to start off with DC analysis for MOSFET transistor circuits. A few lectures before, we studied bipolar junction transistor, and then we did a single example where we force the bipolar to go through different modes of operation. I'm going to do the same thing for MOSFET transistors. The first example we're going to go through is an NMOS transistor circuit. In the last lecture, we started off with few key values. So I just want to write those down first so that we can use them over and over again. One of them is mu n Cox for MOSFET transistor. For NMOS transistor was 136.5 microamps per volt square. Vt of NMOS was 0.5 volts. Cox value was 3.9 femtofarad per micrometer square, and lambda n for the device was 0.05 divided by Ln, volt to the power minus 1, and this Ln is in micrometer. We will be using these values over and over again, and again this was for 0.5 micron CMOS technology. So the first example we are going to go through for MOS DC analysis. Let's write NMOS, very similar to our bipolar example. We have a resistor. So let's say the resistor R1. Resistor R1 will start off with value 2k ohm. For AC input, we will apply a big capacitor here, and then we will apply our V in AC. We already went through the discussion about why we have the C big. Let me repeat that again. We have C big, which is a decoupling capacitor, which isolates our AC source from the node A. The AC source has 0 DC value. Hence, we would like to isolate that from our input point. For frequencies of interest, this capacitor C big looks like a short, and V in is applied directly to the node A. So whenever we are given a circuit like this, first we do a DC analysis, or rather operating point. In this case, voltage at node A, VA, is given by, it's a resistive divider, so 2 kilo ohms divided by 40k plus 2 kilo ohms, and that is equal to multiplied by 1.5 volts. So this would be equal to 0.07 volts. And the reason we look at it as a voltage divider is current going into the gate of the MOSFET, the DC current, is equal to 0. So this makes our life a lot easier when we compare it with the bipolar transistor. In the bipolar case, there is base current flowing, so to deal with the base current, what we had to do was we had to do Thevenin's equivalent of circuit looking over here. In this case also we could do the Thevenin's equivalent, but the value of the voltage, Thevenin voltage, would come out to be this. There will be a Thevenin resistance. However, since the current flowing through that Thevenin resistance is equal to 0, the value VA voltage will be applied directly to the gate. What do you think will happen with VA of 0.07 volt? Which mode of operation is the MOSFET M1 going to be? I would like you to think about it for a second before I give you the answer. VGS for M1 is equal to 0.07 volts. Now this is less than VTN, which is 0.5 volts. So we expect the transistor M1 to be turned off or cut off. M1 will be off, and there will not be any current flowing through transistor M1 from drain to source, as a result of which the output voltage V out will be equal to 1.5 volts minus 7.33K times 0. 0 is the current flowing through the resistor, as a result of which it should be equal to 1.5 volts. In the beginning, I'm going to do these explicit calculations, but over a period of time, they will become second nature to you and you don't have to even think about it. Let's do next example where I'm going to make slight modification. The modification is going to be change the value of the resistor. I'm going to change the value of the resistor to 40K. Now what do you think will happen? We start off with the same analysis. We say VA will be equal to 40K divided by 40K plus 40K times 1.5 volts, and that should be equal to 0.75 volts. Since VA is greater than 0.5 volts, we can say that the transistor is turned on. We don't know yet if it's in saturation or non-saturation region or triode region. So which one should you start from? So we make an assumption, we start off with the saturation, and the reason I like to start with saturation is because the equation for saturation is easy because there is no dependence on the output voltage. So let's start off with that and verify our assumption. So we assume M1 in sat region. Now you have to remember the equation for saturation region, which is IDS is equal to mu n Cox divided by 2 W by L VGS minus VTH n square. We already know from the previous page the mu n Cox value, and we know VTN value, and we know lambda n value. So we are going to put all those things together here. In this particular case, we are ignoring the channel length modulation in the first analysis. Divide by 2. W is equal to 12 microns and L is given to be 0.5 micron multiplied by VGS minus VTH. That would be VGS we just calculated, 0.75 minus 0.5 square, and that would give you volt square. So this will give you, I would like you to do the calculation yourself. Pause the video. So this would be your I drain to source current, assuming the transistor is in saturation, and the output voltage V out will be equal to 1.5 volts minus 102.375 microamps multiplied by our resistance at the drain was 7.33K. So IDS is going to flow here and you will have a IR drop here. IDS multiplied by 7.33K, and that would give you the output voltage. And you can calculate this number will come out to be 0.749 volts. Again, we are computing only DC quantities. Now let's check if our original assumption of M1 being in saturation is correct. Checkpoint for saturation is V drain to source voltage has to be greater than VGS minus VTH. We already know this number. This number is 0.25 volts, and the VDS we have calculated is 0.749 volts. So this assumption is true, so saturation is valid. So we can draw the DC operating point of the circuit, and it's going to look like this. So if you do a SPICE simulation or a circuit simulation and do DC operating point of this particular network, you will see these numbers. One more number you should have here is the current flowing through this. That would be 1.5 volts divided by 80K. That should be 18.75 microamps. Given this DC operating point, now we would like to figure out what is the AC small signal voltage gain. So from previous analysis, we know how much current is flowing through the device, transistor M1. We can draw our AC small signal model here. I would like you to do it yourself. You can pause the video and draw it on your own, a small signal model representing this circuit. So remember, all the DC voltage sources will connect to 0. So assuming you got this right, this is what it should look like. So this would be your gate terminal, this would be your drain terminal, and this is your source terminal. So first thing is we draw the transistor small signal AC analysis model, which is GM VGS, which is here VGS. Again, VGS is a AC quantity here, and we have an output resistance R out for the transistor. We have 7.33K of a load resistor here. That other end of the resistor will be connected to ground, just like the source is connected to ground. It's important to understand why we connected the other end of 7.33K resistor to ground. When we do AC analysis, we look at all the DC bias voltage sources. For example, this 1.5 volts is a DC voltage source. So in AC domain, it doesn't change. Its value is 0. That's why we connect 7.33K to ground. The source is already ground over here. And since we said the C big is large enough to be a short for our frequencies of interest, we can connect it directly to the gate. The resistance, the parallel resistance of 40K and 40K, we can draw it as a 20K over here. But it doesn't participate in our AC analysis because this 20K is driven by input voltage source Vin, which in this case we are assuming as an ideal voltage source. Given this AC analysis representative circuit, now we need to figure out what is the value of GM and R out. Remember, GM and R out, they are small signal parameters, for example, transconductance and output resistance. However, their values are decided by the large signal operating point. In this particular case, there are three different equations we learned in the previous lecture for GM, and the most useful one here, because we already know these values, is 2 IDS divided by VGS minus VTH. So you can compute this yourself. 2 times 102.375 microamps divided by 0.25 volts, and that number will be equal to 0.819 millisiemens. The output resistance R out is given by 1 divided by lambda IDS. 0.05 divided by ln times 102.375 microamps. Since we said ln is 0.5 micron, the value for lambda becomes 0.1 multiplied by 102.375, 10 to the power minus 6 over here, and this should be ohms over here. That will be equal to 98 kilo ohms. One more point I want to bring out again or reiterate is lambda is given by this equation 0.05 divided by ln, volts to the power minus 1. Given is ln is in micron. So for example, if ln is equal to 0.5 micron, then lambda will be equal to 0.05 divided by 0.5, and that would be equal to 0.1 volts to the power minus 1. If ln is equal to 2 microns, let's say we chose ln of 2 micron, then lambda will be equal to 0.05 divided by 2, and that would be equal to 0.025 volts to the power minus 1. If you do Kirchhoff's current law and voltage law, you can figure out the gain of this circuit. This is the output. So V out will be equal to GM times Vin, and the current here is flowing in the downward direction. So we can say minus sign for current flowing in upward direction. That current is going to flow through our two resistors in parallel, R0 and 7.33K. R0 parallel RL. That would be your V out. So the gain expression is V out divided by V in, and that will be minus GM. And what are the two values? RL is equal to 7.33K and R0 is equal to 98K. To do a quick approximation, I'm going to assume that this 98K, I can ignore it compared to 7.33K. Again, this is just for a quick analysis. If somebody asks you in an exam setting or anything like that, you should do the parallel combination of the two resistors. Here it would be 7.33K multiplied by, and that would be minus 0.819 millisiemens multiplied by 7.33 K ohms. So this will come out to be minus 6. So our voltage gain is minus 6. Let's compare this to our bipolar example. You might remember the bipolar number was approximately 100. However, it's unfair comparison because in the bipolar case, our current flowing through the bipolar transistor was 1 milliamp. So we were spending a lot more current over there. Now I'm going to make a small modification to the circuit. Just like before, in the bipolar case, I'm just going to move the decimal point from the drain resistor. So we are going to go from 7.33K to 73.3 K ohms. So if we had done similar analysis like before, assuming M1 in saturation, then our output voltage Vout would have been 1.5 volts minus 73.3 K times 102.375 microamps. And that would have given us value of minus 6 volts. So minus 6 volts at the output DC operating point again is not possible because the lowest voltage that we can have in this circuit is 0. So based on this, we say that the transistor M1 is not really in saturation region. So M1 is in non-sat region or triode or linear region for sure. So what is the equation for the non-saturation region? You should again commit this to memory. IDS is equal to mu n Cox W by L VGS minus VTH times VDS minus VDS square divided by 2. Now we can substitute the values and that would come out to be 136.5 micro multiplied by 24 and 0.25 VDS minus VDS divided by 2 square IDS. We can also rewrite this as 0.819 divided by 1000 VDS minus 1.638 divided by 1000 VDS square. The second equation, this is one equation that we have. The second equation we have is the current flowing here is IDS and output voltage Vout is VDS. In this particular case, we don't know what IDS is and we don't know what VDS is. So we're trying to figure out both the values. So the first equation, we got it assuming non-saturation region operation. The second equation we are going to figure out using Kirchhoff's voltage law. So the second equation is going to be output voltage VDS is equal to supply voltage minus IR drop, which would be 73.3K times IDS. So now we can substitute IDS here in this equation and you will get this is equal to 1.5 volts minus 60 times VDS plus 120 times VDS square. So this should give you a quadratic equation and the two roots of this equation are going to be VDS is equal to 0.482 volts or 0.026 volts. So out of these two roots, if you choose this one, then we know that this is greater than VD sat of 0.25. So this is not a valid root. So this is the only possible solution for non-saturation region. And once we know this, we can calculate the current also using this equation. Since the transistor acts as a resistor, we can say R on of transistor M1 is given by 1 divided by mu n Cox W by L VGS minus VT H, and that will be equal to 5 micro multiplied by 24 multiplied by 0.25, and this would be 1.221k ohms. So this is close to VDS equal to 0. That's when we are calculating this resistance. Interestingly, if you look at this on resistance, then our circuit is going to look just like two resistors, and this would be our VDS. This was 73.3k and this is 1.221k. This is non-sat M1 resistance calculated based on this, and this is 1.5 volts. So you can compute VDS is equal to resistive divider. So this would be R on M1 divided by 73.3k plus R on of M1, and the value comes out to be 0.025 volts, which is very close to 26 millivolts we had already said. So this is another way to look at it. So we just went through an exercise where we put NMOS transistor through cutoff, saturation and non-saturation by playing with couple of resistors, just like what we did in case of bipolar case. So this should give you a good feel for different modes of operation of both the devices. Now we are going to compare both bipolar and CMOS head to head for their maximum usable gain that you can achieve out of them. Now this is something that gives you a perspective in terms of capability of both the devices, and it's an excellent interview question. So what we are going to do is we are going to compare bipolar and CMOS gain. That's what we're going to do. And we're going to keep the same topology. So for example, on the left side, I'll do the bipolar topology. And purpose of this discussion, we will just have a DC voltage source here of biases. And this is our V in. And this would be V out, RL. Bipolar transistors are denoted with Q. Say this is our VDD. For MOSFET, I'm going to draw a circuit on the right side, which is the mistake I made here is this should be called VCC. The reason we call it VCC is because generally the collector is connected to the VCC. And here in the case of MOSFET, it's the drain. That's why it's called VDD. Similarly, the negative potential is called VEE because it's emitter, and the negative potential that you apply in the MOSFET circuit is called VSS because it's the source of the device. However, in all our analysis, we just use ground for simplicity. So in this case would be, this is transistor M1, this is the current I1 flowing, and here also we have RL. And we'll do very similar circuit, which is AC plus DC. The DC bias is to bias the transistor in the right region. One of the most important things that you have to realize is how do you bias your transistors? Where would you bias the output voltage? I want you to think about it. Would you bias them at VCC or ground or somewhere in between? If it's somewhere in between, where would you bias them? I would like you to imagine this picture. This is your VDD voltage or supply voltage, and this is your ground voltage 0. The output voltage is going to swing in these two voltages. So you may have a sine wave that will be going like this at the output. To get the maximum swing out of your amplifier, it's best if you bias your output voltage at half the supply voltage. Okay, so this is VDD divided by 2. Let's say you had biased it close to 0. Then you can only get this much amount of swing. If you had biased it somewhere up in the top, then you will get only this much swing. Because beyond this, this part will get clipped, and beyond this, this part will get clipped. So if you bias it right in the middle, then your output can move. We call it rail to rail, almost rail to rail. So the first observation for both the circuits is the DC output voltage. What should be the DC output voltage? And once you realize that, things become very easy for you. So V out DC is equal to VDD divided by 2 because that gives you the maximum swing, or VCC divided by 2. Now let's do the bipolar AC analysis. For the bipolar transistor, if you remember, let's draw the simple small signal model. And for small signal model, we will remove the DC quantities, and it's going to look like this. we can assume that the output impedance, output resistance of the bipolar is much greater than the load resistance. So the maximum voltage gain V out divided by V in is given by, so I'm going to ignore this part. Maximum voltage gain is going to be equal to minus GM times RL. And what is the value of GM for bipolar transistor? Again, you need to commit that to your memory, at least for the duration of this course, because you'll be using it so many times. It's the current, collector current divided by Vt. What is Vt? Vt is not threshold voltage. Vt is Kt over Q, the thermal voltage, and RL. Now comes the interesting observation. If you look at the numerator, we see IC times RL. What does that indicate? IC times RL. And if we go back to our circuit, IC times RL represents the voltage drop at the output here, IC times RL. And we have already said that output DC voltage is equal to VCC divided by 2. So we know that IC times RL is VCC divided by 2. So this would be equal to minus VCC divided by 2 divided by VT, equal to minus VCC divided by 2 VT. So let's say if we have VCC equal to 2.5 volts, then the maximum gain from BJT is equal to minus 2.5 divided by 2 times 26 millivolts, which is going to come out to be approximately minus 50 if we assume this to be 25 millivolts. Okay, so this is the maximum gain we can get out of a circuit using bipolar transistor. Again, we are looking at ballpark numbers, okay, and it depends on the supply voltage. Let's do exact same analysis for MOSFET transistor. Let's draw the small signal analysis, and it's going to look like this. For MOS, we have input voltage V in that goes to the gate, and then we have drain to source current flowing GM times V in, and here we have R out, output resistance, and again the RL is going to ground because we ground our VDD for AC analysis. Again, here also we can assume that output resistance is much greater than RL. So max voltage gain we can get out of a MOSFET stage is minus GM times RL, load resistor. And what is the formula for GM? The one that we should use for a fair comparison would be one which has I and V, and that would be our exact formula, which is minus 2 IDS divided by VGS minus VTH. That's the GM formula. Multiply that by RL. Now you can interestingly look at this again and draw a similar comparison. You can see that IDS times RL is the voltage drop across the output resistor. Let me go back and show you. So this is IDS times RL would be the voltage drop across this resistor. We already said that the output voltage is biased at VDD divided by 2. So this drop will be also equal to VDD minus VDD divided by 2, which is equal to VDD divided by 2. So 2 times IDS times RL will be equal to VDD divided by VGS minus VTH. So this is the maximum gain we can get out of a MOS stage. So both the formulas look very similar. In one case we have VCC divided by 2 VT, VT being KT over Q. In other case we have VDD divided by VGS minus VTH. In case of bipolar, we have no control over the gain because VT is equal to KT over Q, 26 millivolts, and it's only controlled by the temperature. In case of MOS, we have control over VGS minus VTH, so we can change that value to our desired. Now you may say that, hey, I can take VGS minus VTH equal to 0, and then you got infinite gain, and now my MOSFET transistor amplifier looks much better than the bipolar. However, what does that really mean? VGS equal to VTH. That means that you are operating the transistor very close to cutoff mode. It's almost turned off. Okay. Let's understand this one more time. The concept of VGS minus VTH and how do you choose that value? If you remember, in previous classes, we had plotted square root of IDS on versus VGS on the x-axis. And in that case, we said it's going to, since it's square root of IDS, it should be a linear curve and it would look like this. Something like this, and this would be your VTH. Let's say if this was the point at which you are operating, then this would be your VGS and VGS minus VTH is this distance. And we also call that as VD sat of the transistor, saturation voltage of the transistor. So we have control over VGS minus VTH of the device by changing the DC biasing at the input of the transistor, gate input of the transistor. And the trouble we get into is as we start reducing VGS minus VTH, you are actually traveling in this direction. And as I explained earlier, this part of the curve right here, it's not as abrupt as I have shown it over here. In reality, you have something called subthreshold region operation that's happening over here, and we try to stay away from that region. So this is our subthreshold. So practical value of VGS minus VTH or VD sat is every designer's choice. We can choose a number to be, let's say, 250 millivolts to keep it safely in saturation. Another thing to note is you're applying a sinusoidal input signal on top of this VGS DC bias. So we want to make sure that whatever signal that you're applying, or that doesn't drive the transistor into subthreshold region also. And that's also one more reason why you would like to choose VGS minus VTH to be a little bit larger. So having said this, we can now calculate the value of the MOSFET gain, and that would be for VDD equal to 2.5 volts. The max gain will be minus 2.5 divided by 250 millivolts, and that will be equal to minus 10. So now you can compare the two stages, and you can see that bipolars have inherent advantage because of the VT, which is 26 millivolts, and in MOSFET case, we would like to keep VGS minus VTH to be some minimum value, so that limits our maximum voltage gain that we can achieve.